Hey everybody, I hope you can hear me. I don't have my microphone. I'm using my laptop mic built in, so hopefully you can hear me. I wanted to do a better or more intense network optimization problem to make sure you understand how to get the flows and the duals and the reduced cost and all of that. So let's just jump right in. So I got this network here, and the blue are the supplies and the demand at each node, and in the red are the cost of 1 unit shipping across that arc. So if it's in 1 unit here, it'll cost me 10 from node 2 to 5. Okay, now I haven't shown you how to get a starting solution yet, so let me just jump into an initial network. You would actually find these with something called the two-phase network simplex, or you could probably logic as long as you have all the supplies used up and all the demand shipped and met. I'm going to go ahead and add the root on node 1. All right, and let's see. We will ship all 10 this way. These are now the flows that I'm writing, not the cost, because these are the actual network flows. Where is my first network? I think I want to send these 10 over here since that had a demand of 10. So this is the first one I want to do. So all 6 will go down this way, and then 8 will go down here. So this is a feasible network flow, because let's see if I can get both of these in the screen at the same time. Yeah, so this has a supply of 10, so it sends all 10 to node 2. Node 2 has a supply of 6, so it now is holding 16. It splits those up and sends 10 to node 5, which has a demand of 10, so that demand is met. The 6 gets shipped down to 3. 3 has a supply of 2, so if I ship it 6, it now has 8, and it can send all 8 down to 4 to meet its demand. So this is a feasible flow of a network. Okay, so I'm going to scroll down just so we can look at this network, and what we need to do now are assign the dual values. So I can assign a 0 of a dual down on node 1. Now I need to assign the dual values, the dual variable values, for all these other nodes. Now, picking this 0 is arbitrary. What's really important is the spacing between the dual values. So if you really felt like you could pick 100 or 1,000,000 or your favorite number 4 or -7, it doesn't really matter, but 0 makes arithmetic a bit easier. And remember, this is all based off of the complementary slackness formula that tells if I take the original cost and I subtract the value of the dual variable at the tail of the arc, so we just call that the dual tail, and I add the dual variable at the head of the arc, so the dual head, that should equal 0. And that comes from if I wrote this network as a linear programming problem and then wrote the dual, all the dual constraints are going to have a plus and a minus in them. Okay? So these are the original costs. So I'll need to be able to look back at this network. So you look at it real good, maybe write it down on a piece of paper and pause and write it down. I have it right here beside me on a piece of paper. I'm going to be referring to these costs a whole lot. I need them to figure out all the duals and then to check for what arc is attractive to enter the basis. So the way we calculate the duals is you start at the root, which is, once again, can be arbitrarily assigned. I started it at 1, and we'll do everything from this root. So from there, we kind of follow a chain of what's connected to the one dual we set at 0. So what was the cost of 1 to 2? It was 3. So I can use this formula right here. So the cost, so we're going to do the 1 to 2. The cost there was 3. Let's do this in a different color. 3 minus the dual tail plus the dual head has got to equal 0. Well, because I'm starting from node 1 and going to node 2, kind of using this connected as a chain, I know the dual tail here, the tail of this arc, has a dual value of 0, so I know this one. What I don't know is what the dual head is. Well, 3 minus 0 is 3, so this needs to be, I'll do it in red, -3 for this to equal 0. And so that's how we fill out the duals. This has to be -3. Now from here, I can figure node 5 and node 3 because they are connected to this node 2. That's how I find the duals. So what is the cost of 2 to 5? Cost is 10. So I have 10 minus the dual tail. Do I know the tail this time from 2 to 5? The tail is right here, so yes I do. Minus negative 3 plus, and I need to know, that's what I'm looking for, the dual head has got to equal 0. So the head of this arc ends at 5. So it is 10 minus a negative 3, so that's 13. So this must be negative 13. Oops, let's write it in green here. Negative 13. And I can find the rest of these in that same style. And we might can do these in our head. The cost of 2 to 3 is 2 minus a negative 3. That would be 5. So this dual needs to be negative 5. So you see you can kind of start to do them in your head. The cost of 3 to 4 is 4. So 4 minus a negative 3, minus a negative 5, that makes positive 9, and so this dual needs to be negative 9. So you can write them all out to be meticulous and to make sure you don't make any mistakes. I'm just did those in my head to do them kind of quickly and talk you through them. If you do have questions on how to find duals, please ask. But that's how we can find the duals. Now we can lazily not have to calculate all of them ever again, since we know the spacing between some of these. It'll depend on what arc exits the basis and what arc stays in the basis. Okay? So now it's time to see which arc will enter the basis. And we're actually going to use the same formula that we have here, except for we're going to see what it equals. Okay? We need to know what it equals. And these, whenever we do this, these are for arcs that are not in the basis. This will give us the reduced cost. Reduced cost. And that will tell us which arc is the most attractive, the most negative. And so we have to just do all the arcs that are not in the basis right now. So there are 4 that I need to check. So let me write them down. We have to check x13, see if this one might enter. x14 is a possibility. x35 and x45. Alright, so we need to get the cost on those. Let's see, the cost of 1 to 3 is 3 minus the dual head. The head of the arc is at 1, so minus 0, plus the dual tail. 1 to 3, the dual tail is negative 5. So 3 plus a negative 5 is negative 2. So that one is attractive. Let's see if it is the most attractive. Let's now check 1 to 4. So the cost on 1 to 4 is 4. So 4 minus the dual tail coming from 1. Of course, that's 0. Plus the dual head value. The head's at 4. So negative 9. 4 plus a negative 9 is negative 5. So this one's attractive. It's even more attractive to enter than this one. This will improve our objective function the most. Now let's check 3, 5, and 4, 5 really quickly in the same way. 3 to 5 has an original cost of 3, I believe. The dual tail is negative 5, so 3 minus negative 5. And the dual head of 5 is negative 13. Let's see, 3 minus negative 5, that is positive 8. Plus negative 13, that is negative 5. So I actually have a tie for most attractive right now, unless this one's more attractive, which I don't think it is. Let's do that. 4 to 5 has a cost of 1. It could be. Minus negative, let's see, node 4 has a negative 9. Negative 9. Plus node 5 is a negative 13. So that ends up being a positive 10, negative 13. That ends up being negative 3. So these are the most attractive. So I will just go what's known as lexicographically and just choose the first one here to break a tie. It doesn't matter which one you choose, but this is the most attractive. Well, these two are tied for most, so either of them will work. I'm going to pick this one, and so we will enter x14. So what we're going to do now is go over to our network and draw a dotted line entering in x14. Okay, now that is flowing this direction, right? And that will create, notice it creates a cycle in our network. And we can't have cycles, we have to have this be a minimum spanning tree, or a spanning tree. It needs to connect all the nodes with no cycles, no loops. So this variable is going to enter, it's going to push out one of these other arcs. Which one will it push out? Well, it's going to be one of the arcs on this cycle, and it will be one of the arcs pushing the wrong direction. So this arc comes in from left to right, and then the cycle goes up and back around left like that. Now, the arc that's going to leave will be whatever's pushing the wrong direction but has the smallest value. Okay, so 8 is pushing the wrong direction, 6 is pushing the wrong direction, 10 is pushing the wrong direction. Which one is the smallest of those flows? And the smallest, I guess I'll keep this in red, happens to be this 6 from 2 to 3. So that will leave. So arc 2, 3 leaves the basis. Now, that will give me a new network. Let me try to draw the new network really quickly. And I have had a lot of questions about how to update the new flows. Well, we're going to base it off of the flows that we just had and try to adjust. Okay, so here's how we're going to adjust. Everything on this cycle will change. So the 1 to 4, 3 to 4, 2 to 3, and 1 to 2 will change. 2 to 5 is not going to change. Okay, we did not mess with that flow. Only the flows in the cycle get changed. So we are actually able to direct flow this way by this amount of 6. So if you're going in the direction of this cycle, you're going to get 6 added to you. So for instance, 1 to 4 was at 0, it is now going to be at a flow of 6. If you are flowing in the wrong direction, you're going to get 6 subtracted from you. So this was shipping 10, but notice it is in the wrong direction, so it'll be 10 minus 6 or 4. This node right here was shipping 6 in the wrong direction, so 6 minus 6 is 0, so that is why it is no longer in the network. And this one was shipping 8. 8 minus 6 is 2, so we are now sending 2 this way. So let's do a quick check. That's a very sloppy 2, but yes, that is a 2. Let me see if I can erase it without erasing too much and make it neater looking. So this is a flow of 2. Okay, are we using up our supplies and meeting the demands? Well, yes, we are. If you look, this has a supply of 10, 6, and 2, and we're shipping 10 and 8 to those guys. Well, if I ship 4, so this 10 is being split 4 and 6. So yes, we're using up that 10. This one had 6. It's getting 4, so it has 10. It sends all 10 here. So this is feasible. We're meeting that demand. Node 3 had a supply of 2. It sends all its supply to node 4 with this 6. 6 plus 2 makes 8. So we are, in fact, feasible and all the flows are correct. Okay? So now we have to figure the dual values again. And I got some good news for you. We do not have to refigure all of them. So ignore the red dotted line and look at this last network. Any that stayed connected to the root do not need to be updated. But whatever was cut loose from the root, the 3 and the 4, we cut this arc here, those are the only duals that need to be updated. So 0, -3, and -13 are actually fine and dandy. They stayed connected to the root. But 3 has a new connection to the root now. It's connected over here. So we need to refigure these duals. Now the good news is the spacing between them will not change. So I only need to refigure one of these duals, and I know the other one will change by the same amount. Now how is this connected into the network? It's connected by node 4, 1 to 4. So that's what I will use to calculate the dual on node 4. I will see how much it changed by, and then I can change node 3. Or you can recalculate all of them again if you want to. That's fine too. So let's see, what was the cost of 1 to 4 originally? It was 4. So remember that formula is the cost minus the dual tail plus the dual head, and when I'm finding the duals, it has to equal 0. So the cost was 4 of 1 to 4 minus the dual tail of 0. That means this one must be a negative 4 to equal 0. So that dual is negative 4. What was it in the last pivot? It was negative 9. So this went from negative 9 up to negative 4. It moved by 5. So this one will actually go up by 5 and go up to 0. From negative 5 up to 0. The spacing between these is 4, right? This one's 4 bigger than that one, so it's got to be 4 bigger than that one. So I don't have to figure all the duals. I don't have to refigure any that stayed connected to the root. And any that get disconnected from the root, I only need to figure out one, and it connects to the rest and tells me how the rest are going to change. Okay, so now let's do a few more pivots. We'll just do this a few more times, and we should be at optimal. So what we have to do now is check all the reduced cost again. So let's see, what variables are possible? x13, let's check that one. x23 is a possibility. That just left, so it probably won't pivot back in right now, but it might pivot back in later. We have to be careful, always checking all the values. x35 and x45. I'm getting these arcs that are possible to enter from the original network where it shows which arcs are possibilities. Okay, so let's check these. Let me see, what was the cost on 1 to 3? I believe it was, let's see, I got it over here on a piece of paper. 1 to 3 had a cost of 3. Maybe I'll go ahead and write all the costs down. 2 to 3 had a cost of 2. 3 to 5 had a cost of 3. And 4 to 5 had a cost of 1. Okay. So now we can do minus the dual tail. So 1 to 3, the dual tail of 1 to 3, the dual is 0. And in this case, it's kind of interesting because the head dual is 0 as well, which ends up with a 3. So this is not attractive right now to enter the basis because it's positive. All right. Now let's check 2 to 3. So minus the tail plus the head. So 2 has a node, a dual of negative 3. 3 has a dual of 0. So this one ends up being 5. So once again, not attractive, it's positive 5. Let's check 3 to 5. 3 is 0, so minus 0. Plus 5 has a negative 13 as a dual. That is pretty attractive considering it's at negative 10. 4 to 5 would be minus negative 4 plus negative 13. That will be negative 8. So we have two attractive variables to enter the basis, but this one is the most attractive. So pick the most negative number. So that's the most attractive. So x35 enters the basis. And so we're now just doing these same cycles over and over again. 3 to 5. This is a really interesting cycle it creates. So it's flowing in that way, and do you see it makes a loop all the way back around? So technically, every arc is involved in this loop from 3 back around to 3. Now, any flowing in the wrong direction are candidates to leave, and there happen to be 3 that are flowing in the wrong direction. 2 to 5 is flowing the wrong way. 2 to 1, or 1 to 2 is flowing the wrong way. 1 to 4, that's fine, that's the way we're going. And 3 to 4 is flowing backwards. So what is the smallest of these 3? 10, 4, or 2? 2 is. So this is going to leave the basis. So x34 will leave. Okay, so 3, 5 enters, 3, 4 leaves. And we can update the flows based off of this information. So let me draw the network, or draw the nodes, I guess. All right. The root is still going to stay at 1. And so what we're going to have is, we still have 1 to 4, we still have 1 to 2, we have 2 to 5, and we have 3 to 5. Now, how much were we able to change the flows by this smallest amount in the wrong direction, by 2? Now, everybody happened to be in on that loop that time. So remember, if you're going in the wrong direction, you get 2 taken from you. If you're going in the correct direction, you get 2 added to you. So this one was at 0, it now has a flow of 2. This one was at 10, going the wrong direction, it now has a flow of 10 minus 2, or 8. It's an ugly 8, I'm sorry. 1 to 2 has a flow in the wrong direction. It was 4, it's now going to have 4 minus 2, or 2. In this flow, 1 to 4 was flowing at 6 in the right direction, so it'll direct 8. This one was 2, backed up to 2 minus 2 is 0, so it's out of the basis. Alright, now the important thing to note here is we can check again to see if we're feasible. So remember, not that we have to check. If you do this simplex style of keeping up with all the flows, you don't have to check. But this had a supply of 10. It splits its 10 up. This had a demand of 8, so that demand is met. This had a supply of 6. If it gets 2, 6 plus 2 is 8, and it sends all 8 here. That's good. This had a supply of 2. It sends 2 in. So 8 plus 2 is 10. This had a demand of 10. So all the supplies and demands are used and met. So now we can figure the duals. Now look, we cut right here. These are all still connected to the root. This is connected to the root. 3 is the only one we cut loose. So I actually don't have to refigure. Most of these duals are not going to change. If you wanted to, you could try to refigure them, but they would end up being these same values. I just need to figure out this dual. It is connected to a known dual by this arc 3 to 5. So what is the cost on 3 to 5? 3 to 5 has a cost of 3. So that formula says the cost minus the dual tail, which I do not know, plus the dual head, which is negative 13, has got to equal 0. See, 3 minus, so I need this to equal positive 13 to cancel with this negative 13, so it'll have to be a negative 10. So this dual is negative 10. So there, we are at our next network. So now we can look to update or check all the reduced cost again. So what are some candidates to enter? Well, let's see, 1 to 3 is a possibility. We still have to check it even though it wasn't attractive last time, because with the way we're making adjustments, it could become attractive to enter the basis. I need to check 2 to 3. I need to check, let's see, 3 to 4. And I need to check 4 to 5. And so I need all those costs. Let me see if I can get those costs really quickly without scrolling up. I have it over here beside me. 1 to 3 has a cost of 3. 2 to 3 has a cost of 2. 3 to 4 has a cost of 4. And 4 to 5 has a cost of 1. So now I can do minus the dual tail. Dual tail 1 is 0 to 3. So that's plus negative 10. That will be negative 7. Same thing here, cost minus the dual tail, which happens to be negative 3, plus the dual head, which happens to be negative 10, will give me a cost of, let me scroll a little bit, negative 5. So far, both of these are attractive. 3 to 4, so minus the dual tail, which is negative 10, plus the dual head, so what's the head? 4, negative 4. This is not attractive. So that'll be what? 14 minus 4. That's positive 10. And then finally, 4 to 5. So minus the negative 4 plus a negative 13. That is negative 8. So that right there is our attractive variable to enter the basis. So x45 enters. Okay, now notice the loop it will make will go around this way. I can't quite draw it easily, but it will not affect 3 to 5. It is only going to affect the part that creates the cycle. So 3 to 5 is fine, it's going to stay alone. Now notice, how many do I have flowing in the wrong direction? I have this one that has a value of 8, this one that has a value of 2, and this is flowing in the correct direction. So these are the only two candidates to leave. Which one has a smaller flow? This one does. So x12 leaves the basis. So let's draw our new network. If I were smart, I would have just copied this and just keep pasting it, but that's okay. So 1 to 4 is happening. 4 to 5 is now coming in. 2 to 5, 3 to 5, and 2 to 5. Right, and let's update all the flows. So let's see. So we're changing this cycle by 2. So that got pushed to 0. This will get 2 more, so this will be 10. Because it's flowing in the correct direction, it gets added to it by however much we're changing. This was 0, so plus 2 makes it 2. This is 8, but it's in the wrong direction, so it'll be 6. And this one was not touched by that cycle. It's still just 2. It does not change. Okay, this is still our root, and so this is our new network. We could check to make sure it's feasible. This had a supply of 10. It sends all 10 to 4. This had a demand of 8, so it has 2 extra it can send on here. This had a supply of 2. It's shipping them all here. This had a supply of 6. It's shipping them all here. 6 plus 2 plus 2 is 10. This had a demand of 10. So you see that keeping up with the cycle and either backing the flow up or adding the flow to it keeps us feasible for using supplies and meeting demands. So now let's update the duals. And we can do this pretty simply. So let's see, we cut here, so node 2, 5, and 3 will need to be updated. Node 1 is always 0, and node 4 is still connected. It wasn't cut loose. So I need to update node 2. We might can do this in our head. The cost of 1 to 2 was 3. 3 minus 0 plus negative 3 is what it would have to be to give us a 0 reduced cost. Now, notice it did not change, so that means these are actually not going to change because their spacing has got to be kept the same. And these will not change. Oops, I shouldn't have figured that there. I should have figured that here. This is not connected. That's bad of me. Let's check this one to make sure we're right then. Where's my eraser? Let's see. I just caught that. I wasn't paying attention. So what's the cost of 4 to 5? 4 to 5 has a cost of 1. So the cost of 1 minus this dual here. So minus negative 4, so that'll be 5, so this needs to be negative 5. So let's see, how much did that change by? That changed by 8. So this should be what, negative 2, and this should be positive 5 as our dual values. Whew, that was a close one. I'm glad I caught that mistake before I tried to go any further. That would have been annoying. All right, so those are our new duals. So now, once again, we should check all the reduced costs to see if anybody is attractive to enter the basis. So I have x12 that could come in. I have x13 that could enter. I have x23 and x34. All the missing arcs are possibilities. So let's see, what are the costs on these? 1 to 2 had a cost of 3. 1 to 3 had a cost of 3. 2 to 3 had a cost of 2. And 3 to 4 had a cost of 4. So I need to subtract off the dual tail values, add the dual head values, and see what's attractive. All right. Now let's see, from 1, that has a value of 0, to 2, that has a value of 5, so this is not attractive. This is 3 plus 5, this has a value of 8, so not attractive. Let's try 1 to 3. This is minus 0 plus negative 2, that has a value of 1, not attractive, it's positive. Let's check 2 to 3. 2 to 3, so minus 5 plus negative 2, this one is attractive, it has a value of negative 5. And then let's check to see which one's more attractive, 2, 3, or 3, 4. 3, 4, so minus negative 2 plus 3, so plus negative 4. All right, let's see what that's going to be. That will be 4 plus 2, that'll be 6, plus negative 4, that'll be positive 2. So not attractive, we only have one attractive variable at this step, x23. So x23 will enter. And I think we're almost done. So this one's going to enter in, and notice it creates a little tiny cycle right here. Okay. Now notice there's only one arc flowing against it, so that's naturally the smallest arc flowing against it. So that one will leave. So 2, 5 leaves. So let me draw the network again. And then, let's see, this arc is still there, this arc is still there, this one's still there, this one got added in. Let's update the flows. 1 to 4, 4 to 5, 1 to 4 and 4 to 5 are not in this cycle, so they do not get changed. That is still 10 and 2. Everything in this little triangle right here will get changed by 6. So this gets backed up 6 to 0. This was at 0, it gets added 6. And this was at 2, it gets added 6 more, so that'll become 8. So those are the new flows. If you wanted to check, you'd see that they're feasible, using up all the supplies and meeting all the demands. Now let's do the duals. So we cut right here, so this one, and this one, this one, and this one are still connected. There is no need to update any of those. This is still -4, this is still -5, this is still -2. We only have to update node 2. So the cost of 2 to 3 happens to be what? 2 minus the dual tail, which I don't know this time, plus the dual head, which is -2. So that must need to be 0 then, to equal 0. So this dual value is 0. So we have all the duals. Now we need to check to see if we're optimal. I think we might finally be optimal, but let's check. How do I know when I'm optimal? How can I know when to stop this? I stop it when all the reduced costs are not attractive. When there are no attractive variables to enter the basis. So let's check them all really quickly. 1 to 2, 1 to 3, 2 to 5, and x 3 to 4. Let's get all the cost really quickly. 1 to 2 has a cost of 3. 1 to 3 has a cost of 3. 2 to 5 has a cost of 10. And 3 to 4 has a cost of 4. So now we can go about finding the rest of these reduced costs. So let's see, 1 to 2. So minus the dual head plus the dual tail, that equals 3. Not attractive. That's good. So 3 minus the dual tail plus the dual head, that equals +1. Not attractive. Good. 2, 5 minus the dual tail plus the dual head. Thank goodness, that ends up being +5. Not attractive. We're doing good here. And finally 3 to 4. Maybe we're optimal. Let's check. 4 minus the dual tail, so minus a -2, plus the dual head, and that will equal +2. So no attractive. So we are finally optimal. No attractive variables. To enter. So we are optimal. Now you may want to get the optimal objective function value, and you could have kept up with it the whole time, updating it at each step, but it's not hard just to calculate it here at the end. You just need to take each flow, so the flow of 1 to 4 has a flow of 10, and multiply it by whatever its cost was. So what was the cost of 1 to 4 had a cost of 4. Okay, scroll all the way back down. And add that to the cost of each node. So we have 2 to 3 has a flow of 6. The cost of 2 to 3 was 2. Let's see, 3 to 5 has a flow of 8. The cost of 3 to 5 was 3. Let's see, 1, 2, 3, 4. I got one more. 4 to 5 has a flow of 2. The cost was 1. There, I believe I got everything. And you just need to figure that out. What is that? 40 plus 12 plus 24 plus 2. What's that? 52 plus 26. 78 is the objective function value. And these are your optimal flows. So I hope this helped a little bit more, just giving a bigger example with more pivots in it. If you have any questions, feel free to email me. Have a great weekend, guys.